What is mass, really? Welcome, fellow travelers, through the cosmos of contemplation to the Yawning Theories. Here, our grand voyages into the depths of understanding often commence not with a thunderous fanfare, but with the subtle, the seemingly ordinary. Tonight, under the gentle glow of quiet inquiry, we embark on an illuminating exploration of mass, a concept so foundational it underpins the very fabric of our existence, yet one that, upon closer inspection, remains veiled in surprising complexities and profound mysteries. This meticulously crafted video serves a dual purpose: to offer both serene relaxation and stimulating intellectual engagement. We extend a heartfelt invitation for you to delve with us into the intricate, almost balletic dance of gravity, exploring its profound influence on everything from the orbits of planets to the very fabric of space-time. Journey into the mysterious, often elusive world of fundamental particles, uncovering the building blocks of matter and energy, from quarks and leptons to bosons that mediate forces. Furthermore, ponder the expansive, pervasive influence of cosmic fields, gravitational fields, electromagnetic fields, and even more exotic fields that permeates the universe, shaping its evolution and governing its interactions. All these profound concepts are delivered in a voice specifically designed to soothe and calm, rather than to excite or agitate, creating an atmosphere conducive to thoughtful reflection and a deeper understanding of the cosmos. Our aim is to foster an environment where complex scientific principles can be absorbed with ease, allowing for both intellectual growth and a sense of tranquility. Our overarching objective is to enrich your comprehension of fundamental cosmic principles. We sincerely hope that this celestial exploration does not disrupt your natural sleep patterns. However, should this cosmic voyage prove to be a compelling and captivating experience that extends into the late hours, rest assured that you will awaken with a wealth of impressive and thought-provoking knowledge. These profound insights will serve as perfect additions to your casual conversations, perhaps while enjoying a comforting cup of tea. They will enable you to gracefully integrate fascinating details about the universe into your everyday interactions, fostering a deeper appreciation for the wonders that surround us. Our global community is at the heart of everything we do, and we deeply value each individual who joins us. To celebrate this vibrant connection, we extend a warm invitation for you to share your location in the comments below. It brings us profound joy and inspiration to witness our ever-expanding network of listeners engaging and interacting from every corner of the world. This shared experience weaves a beautiful tapestry of curiosity that spans continents, breaking down geographical barriers and fostering a true sense of global unity. Seeing the diverse array of places our audience calls home reinforces our commitment to creating content that resonates with people from all walks of life. Your participation not only enriches our community, but also provides invaluable insights into the global reach of our shared interests. We eagerly anticipate learning more about where you are tuning in from and continuing to grow this remarkable worldwide connection. Should this unique exploration, a harmonious blend of rigorous scientific inquiry and captivating narrative storytelling, resonate with you on any level, be it through a sudden surge of joy, a profound awakening of insight, or simply a fleeting moment of serene contemplation, we would be profoundly grateful for your consideration in showing your support. Simple yet incredibly impactful gesture, liking this video, serves as a vital affirmation, helping us to gauge the reach and impact of our content and to refine our approach in future endeavors. Furthermore, by subscribing to our channel, you become an integral part of our burgeoning community, a collective of curious minds united by a shared passion for discovery. Your invaluable support is the bedrock upon which our mission rests, enabling us to transcend boundaries and reach a wider audience of inquisitive, perhaps even slumbering, intellects. This support empowers us to cultivate a broader and more profound appreciation for the boundless wonders and intricate workings of the universe that surrounds us. We extend our deepest gratitude for joining us on this voyage, a journey that is at once tranquil in its contemplation and intellectually stimulating in its pursuit of knowledge. It is through your engagement that we continue to explore, to learn, and to share the awe-inspiring tapestry of the cosmos. Tonight's primary focus is the deceptively simple, yet profoundly complex, concept of mass. It is an intrinsic property of all matter, omnipresent and profoundly influencing every aspect of our lives, from the monumental celestial bodies that dictate the rhythm of the cosmos, to the minuscule particles that make up the very air we breathe. Yet, the more we scrutinize it, the more enigmatic it becomes, revealing layers of theoretical and practical implications that challenge our intuitive understanding. So, we invite you to settle into your most comfortable space. Perhaps dim the lights and allow the gentle hum of the universe to lull you into a state of relaxed contemplation. Take a deep, calming breath, allowing the tension to dissipate from your shoulders and a sense of tranquility to wash over you. As your mind gently drifts, prepare to embark on an enlightening journey through the fascinating world of mass, its definitions, its manifestations, and its enduring mysteries. A gentle but crucial reminder: this video is intended purely for relaxation and educational enrichment. While it delves into scientific concepts, it is not, and should not be considered, a substitute for professional medical advice, particularly concerning the diagnosis or treatment of conditions like insomnia, anxiety, or any other health-related concern. For any such medical concerns, please always consult a qualified medical professional who can provide personalized guidance and care. Your well-being is paramount. The everyday encounter with mass, more than just heft. When we think of mass in our daily lives, our minds often jump to a simple intuitive understanding: heft or weight. We gauge the mass of an object by how heavy it feels in our hands, or how much effort it takes to lift. A bowling ball clearly has more heft than a feather, and thus we instinctively attribute a greater mass to it. This everyday experience, while a useful starting point, barely scratches the surface of what mass truly represents in the grand scheme of physics and the universe. Beyond the simple sensation of weight, mass plays a fundamental role in countless phenomena we observe and interact with. Consider the momentum of a moving car, the force required to accelerate a train, or the gravitational pull that keeps our feet firmly planted on the earth. All these phenomena are inextricably linked to mass, demonstrating its far-reaching influence beyond mere heft. Tonight we will delve deeper into these nuances, exploring the multifaceted nature of mass and how it shapes the very fabric of our existence. Remember that sudden, jarring resistance you feel when attempting to hoist a suitcase that's far heavier than it looks. That quiet, unyielding protest from your muscles, that, in its simplest manifestation, is mass making its presence known. It's not a flashy phenomenon, yet it is an ever-present force in our lives, subtly asserting itself when you lug a bag of groceries, when you gratefully sink into the comforting embrace of a soft couch, or even when you engage in the delicate, often futile dance of trying to dislodge a sleeping cat from your laptop. Mass, in essence, is the silent, ubiquitous partner in every single interaction involving matter. A constant companion that, despite its profound influence, proves surprisingly elusive when we attempt to pin down a precise definition. To truly grasp mass, we must move beyond its immediate sensory impact and consider its fundamental role in physics. It is the intrinsic property of matter that quantifies its inertia, its resistance to changes in motion. A massive object requires a greater force to accelerate, to decelerate, or to alter its direction. This inertial property is why that deceptively heavy suitcase fights against your efforts. It possesses a significant amount of mass, and therefore a significant amount of inertia. Beyond inertia, mass is also the source of gravitational attraction. Every object with mass exerts a gravitational pull on every other object with mass. While this force is often negligible on a human scale, the gravitational pull between you and a teacup is infinitesimally small. It becomes profoundly significant when dealing with celestial bodies. The immense mass of the Earth keeps us grounded, and the even greater mass of the Sun holds our planet in its orbit. Furthermore, mass is deeply intertwined with energy, as famously articulated by Einstein's iconic equation, E equals mc2. This revolutionary concept reveals that mass and energy are interconvertible. A tiny amount of mass can be transformed into a tremendous amount of energy, as seen in nuclear reactions, and conversely, energy can manifest as mass. This relationship underscores the fundamental nature of mass not merely as a measure of stuff, but as a concentrated form of energy. Despite its pervasive influence and foundational importance in physics, precisely defining mass remains a subtle challenge. We can measure it with great accuracy, observe its effects in countless phenomena, and describe its various manifestations. Yet, attempting to isolate a single universally accepted definition that encompasses all its facets often leads to a deeper appreciation of its complexity. Is it merely a measure of the amount of matter, or is it a fundamental property related to the Higgs field, giving particles their inherent inertia? The ongoing exploration of these questions continues to refine our understanding of this most fundamental property of the universe, reminding us that even the seemingly simple concept of heaviness holds profound scientific mysteries. Let's immediately address a common misconception that often blurs our understanding: the erroneous interchangeability of mass and weight. In the precise lexicon of physics, these two concepts are fundamentally distinct, despite their frequent conflation in everyday language. Understanding this distinction is not merely a semantic exercise. It is crucial for a deeper comprehension of how objects interact with the universe around them. Mass is an intrinsic scalar quantity that measures the amount of stuff contained within an object. More accurately, it is a measure of an object's inertia, that inherent resistance it offers to any attempt to alter its state of motion, whether it's at rest or already moving. This resistance is quantified by Newton's second law of motion, where force equals mass times acceleration, F equals ma. A more massive object requires a greater force to achieve the same acceleration, or experiences a smaller acceleration for the same applied force. Crucially, an object's mass remains constant regardless of its location in the universe, be it on Earth, the Moon, or in the vast emptiness of interstellar space. It is a fundamental property of the object itself, reflecting the quantity of matter, protons, neutrons, electrons it comprises. Its standard unit of measurement in the International System of Units (SI) is the kilogram kg. Weight, conversely, is not an intrinsic property of the object itself, but rather a force exerted upon that mass by gravity. It is a vector quantity, possessing both magnitude and direction, always pointing towards the center of the gravitational body. The magnitude of this force is directly proportional to both the object's mass and the strength of the gravitational field it is in. This relationship is often expressed as weight equals mass times acceleration due to gravity, W equals mg, where g represents the local acceleration due to gravity. On Earth, the average value of g is approximately 9.81 meters per second squared, ms2. Therefore, an object with a mass of 1 kilogram would have a weight of roughly 9.81 newtons n on Earth. The C unit for weight, being a force, is the Newton. To illustrate this crucial difference, imagine the thought experiment of taking a simple spring scale to the Moon. Consider a person with a mass of, say, 70 kilograms. If this person were to stand on a conventional bathroom scale on Earth, their weight would register approximately 686.7 newtons 70 kgs, 9.81 ns2. Now, transport this same person and the spring scale to the Moon. Your mass, the intrinsic quantity of matter comprising your body would remain absolutely identical at 70 kilograms. However, your weight, the gravitational force pulling you downward, would significantly decrease. This is because the Moon's gravitational field is considerably weaker than Earth's, with an acceleration due to gravity of about 1.62 ms2. Consequently, the person's weight on the Moon would be approximately 113.4 newtons, 70 kgs, 1.62 ms2, which is roughly 1/6 of their Earth weight. The spring scale would reflect this reduced force, showing a much lower reading. This thought experiment powerfully highlights that while mass is an unchanging measure of an object's substance, weight is a variable force dependent on the local gravitational influence. This distinction between mass and weight is not merely academic. It is of paramount importance across a myriad of scientific and engineering disciplines, and indeed in our everyday lives. For engineers, particularly those in aerospace, this fundamental difference forms the bedrock of their meticulous designs. Consider the intricate process of designing spacecraft, where every single ounce of mass holds profound implications. Mass directly influences momentum, dictating the inertia a spacecraft possesses and the force required to alter its velocity. This in turn has a cascading effect on fuel consumption. A more massive spacecraft demands significantly more propellant to achieve a desired thrust and trajectory. Furthermore, the precise understanding of a spacecraft's independent behavior dictated by its mass is critical for accurate orbital mechanics and safe navigation through the vast expanse of space. Astronauts, living and working in the microgravity environment of space, experience this distinction in an acutely personal way. While they are effectively weightless in orbit, their mass remains constant and stubbornly resists changes in motion. An astronaut attempting to move a large piece of equipment in the International Space Station quickly learns that even without the pull of gravity, the object's mass still dictates the effort required to accelerate or decelerate it. This tangible experience underscores that mass is an intrinsic property of matter, independent of any gravitational field. Even the seemingly effortless act of walking, a seemingly simple human locomotion, is in fact a highly complex and intricate dialogue with your own mass. Each step involves a precise transfer of momentum as your body shifts its center of mass to maintain balance and propel itself forward. This continuous interplay between your body's mass and the forces you exert against the ground is a testament to the sophisticated biomechanics at play. This intricate dance beautifully explains why a toddler's first steps are often a delightful, albeit wobbly, display of unsteady equilibrium. Their nascent motor skills are still developing, and they are learning to master the complex art of controlling their center of mass and transferring momentum with each tentative stride. Conversely, older adults, having honed a lifetime of balance and spatial awareness, often move with a more deliberate and cautious gait. Their movements are a reflection of years of practice and adaptation, demonstrating a finely tuned understanding of their own mass and how to manage it efficiently to prevent falls and maintain stability. This everyday example, often taken for granted, powerfully illustrates the pervasive and critical nature of understanding mass in all its manifestations. Gravity, an invisible force that governs the universe, is fundamental to understanding how everything from apples falling from trees to planets orbiting stars behaves. It is the natural phenomenon by which all things with mass or energy, including planets, stars, galaxies, and even light, are brought toward or gravitate toward one another. At its most basic, gravity is a force of attraction. The more mass an object has, the stronger its gravitational pull. Similarly, the closer two objects are, the stronger the gravitational force between them. This is why you are pulled towards the Earth, which has immense mass, and why planets orbit the Sun, a truly massive celestial body. Sir Isaac Newton, in the late 17th century, formulated the law of universal gravitation, which mathematically describes this force. His theory stated that every particle of matter in the universe attracts every other particle with a force directly proportional to the product of their masses, and inversely proportional to the square of the distance between their centers. This groundbreaking work provided a unified explanation for terrestrial gravity and the motions of celestial bodies, marking a pivotal moment in the history of science. Centuries later, Albert Einstein presented a revolutionary new understanding of gravity with his theory of general relativity. Instead of viewing gravity as a force acting at a distance, Einstein proposed that gravity is a manifestation of the curvature of spacetime caused by the presence of mass and energy. Imagine a bowling ball placed on a stretched rubber sheet. It creates a depression, and any marbles rolling nearby will be drawn towards it, not by a direct force, but by the curvature of the sheet. Similarly, massive objects like stars and planets warp the fabric of spacetime around them, and other objects follow these curves, appearing to be pulled by gravity. This more nuanced understanding explained phenomena that Newton's law could not, such as the anomalous precession of Mercury's orbit and the bending of light by massive objects' gravitational lensing. Einstein's theory also predicted the existence of gravitational waves, ripples in spacetime caused by accelerating masses, which were directly detected in 2015, further validating his remarkable insights. Gravity plays a crucial role in the formation and evolution of the universe. It was the force that gathered primeval matter into stars and galaxies, and it continues to shape their interactions. Without gravity, there would be no planets, no stars, and no structure to the cosmos as we know it. From the smallest particles to the largest cosmic structures, gravity is the invisible architect of the universe. Gravity, the invisible architect of our cosmos, plays an undeniably significant role in our daily, tangible relationship with mass. Every time you exert effort to lift an object, you are directly working against the incessant downward pull of Earth's gravitational field. The upward force you apply must precisely counterbalance the object's weight, which is fundamentally derived from its mass, multiplied by the acceleration due to gravity, approximately 9.8 ms2 on Earth's surface. This elegant relationship explains why a delicate feather and a dense brick possess vastly different hefts in our everyday experience, even though, in a vacuum, they would famously descend at precisely the same rate. This fundamental principle, eloquently demonstrated by Galileo Galilei, underscores the distinction between mass, an intrinsic property of matter, and weight, a force dependent on both mass and gravity. We often only become acutely aware of our own mass when it becomes an inconvenient, resistant factor. Consider the strenuous exertion of running uphill, where your muscles must overcome both the incline and the downward pull of gravity on your body's mass, or the challenging act of trying to stand upright after prolonged periods of sitting, where your core muscles engage to stabilize your mass against the ever-present force of gravity. Mass undeniably makes its stubborn, persistent presence known whenever we confront acceleration, whether it's the initial jolt felt when a vehicle starts moving, the significant resistance felt while abruptly stopping, requiring the application of a decelerating force, or the subtle shift required to change direction, demanding a centripetal force to alter the path of your mass. In essence, mass is inertia, the inherent resistance of an object to any change in its state of motion. It is this inertia that we feel as a persistent force, a fundamental characteristic of matter that shapes our physical interactions with the world around us. The visceral, unadulterated experience of mass in motion is perhaps most vividly illustrated by the instinctive struggle to intercept a heavy box as it teeters precariously and begins to slide from a shelf. This scenario represents a primal, unmediated confrontation with the fundamental principle of inertia. Inertia, the resistance to change. An in-depth exploration change is an inherent and inevitable aspect of life, yet it frequently encounters profound resistance. Whether in personal habits, organizational structures, or societal norms, the human inclination to cling to the familiar often presents a significant hurdle to progress and adaptation. Understanding the multifaceted reasons behind this resistance is crucial for effectively navigating and facilitating transformation. One of the primary drivers of resistance is the fear of the unknown. Humans are creatures of habit and routine, finding comfort and security in predictability. When faced with a departure from established patterns, individuals often experience anxiety and uncertainty. The imagined negative consequences of change can outweigh the potential benefits, leading to a strong desire to maintain the status quo. This fear can manifest as worries about job security, loss of control, increased workload, or the need to learn new skills. Closely related to the fear of the unknown is the loss of comfort and competence. People often develop routines and methods that make them feel proficient and secure in their abilities. Change, especially when it involves new tools, processes, or responsibilities, can disrupt this sense of mastery. The prospect of feeling incompetent, making mistakes, or having to expend extra effort to relearn can be a powerful deterrent. Individuals may perceive the change as an invalidation of their past efforts or a threat to their established identity. Furthermore, vested interests frequently contribute to resistance. Individuals or groups who benefit from the current system, whether financially, socially, or politically, may actively oppose changes that threaten their advantages. This can involve defending established power structures, protecting resource allocations, or preserving traditional ways of working that favor certain individuals or departments. Such resistance is often strategic and can be highly effective in delaying or outright blocking desired transformations. Another significant factor is inertia and complacency. When things are perceived as good enough, there can be a lack of motivation to embrace change. This complacency can stem from past successes, a comfortable routine, or simply a lack of awareness of the need for improvement. Overcoming inertia requires a compelling vision of the future and a clear articulation of the benefits of the proposed changes, often highlighting the potential negative consequences of not changing. A pervasive lack of communication and understanding often serves as a foundational impediment to progress and harmony in various contexts, from interpersonal relationships to large-scale organizational endeavors. This deficiency manifests in numerous ways, each contributing to a cycle of misinformation, misinterpretation, and ultimately dissatisfaction or failure. At its core, a lack of communication can stem from insufficient information exchange, where critical details are either withheld, omitted, or not disseminated effectively. This can lead to individuals or groups operating with incomplete pictures, making decisions based on faulty assumptions and failing to anticipate challenges or opportunities. Furthermore, when communication channels are unclear, inaccessible, or non-existent, the flow of information is severely hampered, creating informational silos and hindering collaborative efforts. Beyond the mere absence of information, a lack of understanding arises when messages, even if delivered, are not interpreted as intended. This can be due to various factors. Varying perspectives and cognitive biases. Individuals bring their unique experiences, values, and preconceived notions to every interaction, which can filter and distort the meaning of incoming messages. Ambiguity in language. Emotional barriers. Strong emotions, whether positive or negative, can cloud judgment and prevent an objective reception of information. Defensive reactions, anger, or even overenthusiasm can lead to messages being heard through an emotional filter rather than a rational one. Nonverbal cues. The absence or misinterpretation of nonverbal signals, body language, tone of voice, facial expressions, can significantly alter the meaning of spoken words, leading to misunderstanding. In digital communication, where these cues are often absent, the risk of misinterpretation is even higher. Differing assumptions. People often operate under unstated assumptions about the context, goals, or intentions of others. When these assumptions diverge, even well-intentioned communication can lead to unintended outcomes. The consequences of this dual deficiency are far-reaching. In personal relationships, it can erode trust, foster resentment, and lead to unresolved conflicts. In professional settings, it can result in decreased productivity, missed deadlines, duplicated efforts, and a decline in morale. Strategic initiatives can falter when teams are not aligned, and customer satisfaction can plummet when their needs are not accurately understood. Ultimately, a persistent lack of communication and understanding creates an environment ripe for inefficiencies, errors, and an overarching sense of disconnect, hindering growth and preventing the achievement of shared objectives. Also plays a critical role in fostering resistance. When individuals are not adequately informed about the reasons for change, its implications, or how they will be supported through the transition, they are more likely to fill the information void with speculation and fear. Without a clear narrative and opportunity for dialogue, rumors can spread, and misunderstandings can solidify into strong opposition. Effective communication, transparency, and opportunities for feedback are essential to build trust and mitigate resistance. Finally, our collective history is often shaped by past negative experiences with change. These experiences, whether personal or organizational, can leave lasting imprints, influencing our current perceptions and approaches to future transformations. For individuals, a failed career pivot, a difficult relocation, or a challenging adaptation to a new technology can create a deep-seated apprehension towards anything that disrupts the familiar. This apprehension often manifests as resistance, a cautious skepticism, and a reluctance to embrace novel ideas or methodologies, even when they promise improvement. On an organizational level, a poorly managed restructuring, a product launch that flopped, or a failed digital transformation initiative can breed cynicism and a lack of trust among employees. Such experiences can lead to a culture where change is viewed with suspicion, as an imposition rather than an opportunity. The collective memory of past failures can foster a "we've tried that before" mentality, making it exceedingly difficult to gain buy-in for new strategies. This historical baggage can also manifest in a reluctance to invest in new training, a tendency to cling to outdated processes, and a general inertia that stifles innovation and adaptation. Understanding these past negative experiences is crucial for navigating future changes effectively. It requires acknowledging the emotional and practical impact of previous setbacks, addressing underlying fears, and building a narrative of successful change to counterbalance the weight of past failures. Ignoring these historical patterns is akin to trying to sail without understanding the currents. It will inevitably lead to further challenges and potentially to repeating the very mistakes that created the initial negative experiences. Can create a strong predisposition to resist future transformations. If previous change initiatives have been poorly managed, resulted in negative outcomes, or were perceived as disingenuous, individuals will naturally be skeptical and resistant to new proposals. This learned resistance highlights the importance of thoughtful planning, empathetic leadership, and demonstrable success in implementing change. In conclusion, resistance to change is a complex phenomenon driven by a confluence of psychological, social, and organizational factors. Recognizing these underlying causes is the first step toward developing effective strategies for managing and overcoming resistance, ultimately paving the way for successful adaptation and growth in an ever-evolving world. At its core, inertia is the inherent property of matter to resist any change in its state of motion. An object at rest tends to remain at rest, and an object in motion tends to stay in motion with the same speed and in the same direction, unless acted upon by an external force. This fundamental concept, first formally articulated by Galileo Galilei, and later codified by Isaac Newton in his first law of motion, is a cornerstone of classical mechanics. Consider the heavy box on the shelf. Before it begins to slide, it is at rest. Its inertia dictates that it will remain at rest, unless a force, such as a jostle, a vibration, or the pull of gravity on an uneven surface, overcomes its inherent resistance to motion. Once it begins to slide, its inertia then dictates that it will continue to move in that direction and at that speed, unless another force intervenes. The instinctive struggle to catch the box highlights this resistance. When you reach out to stop it, you are applying a force to counteract its existing motion. The heavier the box, i.e., the more mass it possesses, the greater its inertia, and consequently, the more force you must exert to bring it to a halt or change its trajectory. This is why catching a feather falling from a shelf is effortless, while stopping a heavy box requires significant effort and can even be dangerous. The experience is a direct, unfiltered demonstration of the relationship between mass, inertia, and the forces required to alter an object's state of motion. It's a testament to the continuous, subtle interplay of physical laws that govern our everyday interactions with the world. In the realm of classical mechanics, few concepts are as fundamental and intertwined as mass and inertia. Mass, often colloquially understood as the amount of matter in an object, serves as a quantitative measure of its inherent resistance to changes in its state of motion. This resistance, known as inertia, is a universal property of all matter, a foundational principle that dictates how objects behave when forces act upon them. The greater an object's mass, the more pronounced its inertia, and consequently, the more profoundly it resists any attempts to alter its current state of motion, whether that state is one of rest or uniform velocity. This intrinsic stubbornness is why a massive truck requires a considerably longer distance and more force to come to a complete stop compared to a lightweight bicycle. The truck, possessing significantly more mass, exhibits a far greater inertial tendency to continue its motion, demanding a much larger opposing force and duration to overcome its momentum. Similarly, the seemingly simple act of pushing a refrigerator across a room transforms into a Herculean task requiring immense effort. The refrigerator's substantial mass means it has high inertia, stubbornly opposing the initial push to set it in motion, and then resisting any subsequent attempts to increase or decrease its speed. This principle extends beyond mere translational motion. Inertia also dictates an object's resistance to rotational changes. A massive flywheel, for instance, requires considerable torque to accelerate its spin, and once spinning will continue to do so for a long time due to its high rotational inertia, making it an effective energy storage device. In essence, inertia is the universe's way of upholding the status quo for any given object, ensuring that it remains in its current state of motion unless acted upon by an external force. This foundational understanding of mass and inertia is not just an academic curiosity. It is a crucial concept that underpins countless real-world applications, from the design of braking systems in vehicles to the trajectory of celestial bodies. Inertia, at its core, embodies mass's inherent resistance to changes in its state of motion. It's a fundamental property, a silent but powerful declaration of no thank you to any external force attempting to alter its speed or direction. This elegant reluctance means that an object at rest prefers to stay at rest, and an object in motion tends to remain in motion with the same velocity, unless acted upon by an unbalanced force. The greater an object's mass, the more significant its inertia, and consequently, the more effort required to get it moving or to bring it to a stop. Beyond its role as a motion-defying force, mass also imbues an object with its oomph, a delightful term for momentum. Momentum, a vector quantity, is precisely defined as the product of an object's mass and its velocity, p equals mv. This relationship highlights that both the quantity of matter mass and its speed velocity contribute to an object's moving power. Consider the striking contrast between a slow-moving, massive bowling ball and a lightning-fast, but feather-light, ping-pong ball. Despite its leisurely pace, the bowling ball possesses substantially more momentum due to its immense mass. This is a fact intuitively understood by anyone who has ever had the misfortune of finding themselves precariously in the path of either. The impact of the bowling ball, though slow, is undeniably more forceful and potentially more damaging than that of the rapidly moving ping-pong ball. This profound influence of mass becomes particularly evident in the dynamic realm of collisions. When two objects collide, the sheer mass propelling the motion of each dictates the outcome, particularly which object will be pushed back farther. In an inelastic collision, where kinetic energy is not conserved, the object with greater initial momentum, the principles of conservation of momentum govern these interactions, emphasizing that the total momentum of a closed system remains constant before and after a collision. Thus, in the intricate dance of colliding bodies, mass stands as a profound and unwavering determinant of impact and resultant motion. Our continuous and undeniable interaction with mass in our daily lives often leads us to overlook a deeper contemplation of its fundamental, true nature. The temptation to simply categorize it as stuff, a tangible quantity, is almost irresistible. However, this seemingly straightforward explanation quickly crumbles upon closer, more rigorous inspection, revealing a concept far more intricate and profound than initially perceived. We experience mass through gravity, inertia, and the physical presence of objects, yet these interactions only scratch the surface of its true essence. To truly understand mass, one must delve into the realms of quantum mechanics and relativity, where its properties are intricately linked to energy, space-time, and the very fabric of the universe. This journey of deeper understanding challenges our intuitive notions and opens up a fascinating exploration of one of the most fundamental concepts in physics. At the atomic level, matter is, astonishingly, mostly empty space. Its incredibly dense nuclei are held together by mysterious invisible forces, yet somehow these invisible, almost ethereal bits coalesce and combine to create something as tangible as a car that can be dented or a coffee mug that can topple over. There's a curious, almost poetic elegance in how mass, through its very resistance, literally and figuratively anchors us to reality. Without its ubiquitous presence, there would be no resistance, no weight, no friction, and arguably very little fun. Imagine a world where every step you took resulted in an uncontrolled slide, where every object you tried to hold slipped effortlessly through your grasp. This chaotic existence highlights the fundamental role mass plays in our everyday experiences, providing the necessary opposition for interaction and progress. Consider the simple act of walking. It relies entirely on the friction between your shoes and the ground, a direct consequence of the mass of both you and the earth. Without this interaction, you would exist as a dazzling but disconcertingly useless cloud of particles, akin to glitter whimsically spilled in the vacuum of space, floating aimlessly and without purpose through the vast, indifferent void. This fantastical image underscores the profound impact mass has on our ability to navigate and interact with the world around us. It is the silent, pervasive force that defines the boundaries of our physical existence, enabling everything from the delicate touch of a fingertip to the colossal impact of a meteor. The universal language of mass, measurement, and consistency. The consistency of mass is not just a philosophical concept. It's a cornerstone of the physical sciences and the foundation of our technological advancements. Its precise measurement allows us to build bridges that withstand enormous forces, design aircraft that defy gravity, and develop intricate microchips that power our digital world. From the kilogram standard that governs international trade, to the precise calculations in astrophysics that map distant galaxies, mass provides a universal language for understanding and quantifying the physical universe. Its unchanging nature, independent of location or external forces, makes it an invaluable constant in our ever-evolving understanding of reality. Our understanding and quantification of mass extend far beyond the everyday experience of a bathroom scale. The methods employed by scientists are diverse and incredibly precise, ranging from highly sensitive laboratory instruments to the grand observations of celestial mechanics. In controlled environments, scientists utilize highly sensitive balances to measure mass with remarkable accuracy. These instruments, often operating in vacuum conditions to minimize air resistance and buoyancy effects, can detect minute differences in mass, crucial for chemical reactions, material science, and pharmaceutical development. Modern analytical balances, for instance, can measure down to micrograms, a testament to their engineering precision. Beyond static measurements, sophisticated accelerometers play a vital role in determining mass, particularly in dynamic systems or when dealing with objects in motion. By measuring the force required to accelerate an object and knowing the applied force, one can calculate its mass using Newton's second law, F equals ma. This principle is applied in various fields, from testing the integrity of vehicle components to understanding the biomechanics of human movement, and even in space exploration to measure the mass of spacecraft and payloads. Perhaps the most awe-inspiring methods of mass determination involve the intricate principles of orbital mechanics. Gravitational interactions govern the movements of celestial bodies, and by meticulously observing these movements, scientists can infer the mass of otherwise unmeasurable objects. We have, with remarkable precision, weighed entire planets by studying the subtle movements of their orbiting moons. The orbital period and radius of a moon are directly related to the mass of the planet it orbits. This elegant application of Kepler's laws and Newton's law of universal gravitation allows us to determine the mass of gas giants, rocky planets, and even dwarf planets within our solar system. Furthermore, the same principles extend to the cosmic scale. Scientists have estimated the immense mass of distant stars by detecting their characteristic wobbles caused by the gravitational tug of unseen companions. This radial velocity method, where the star's light exhibits a Doppler shift as it moves towards and away from us due to the gravitational pull of an orbiting planet, has been instrumental in discovering countless exoplanets. The amplitude and period of the stellar wobble provide crucial data to calculate the mass of the orbiting exoplanet. Similarly, the gravitational lensing effect, where the light from a distant object is bent by the gravity of an intervening massive object, also provides insights into the mass of galaxies and dark matter halos, allowing us to weigh structures on a cosmic scale. In essence, the quantification of mass is a multifaceted scientific endeavor, employing a spectrum of ingenious techniques that bridge the microscopic world of laboratory experiments with the vast gravitationally governed expanse of the universe. Mass, in its quiet power, doesn't need to loudly announce itself. Its profound and measurable effects make its presence utterly impossible to ignore. Its universal behavior is in itself a thing of profound beauty. Mass remains absolutely constant, whether you are standing triumphantly on a mountaintop in Peru, where the air is thin and the views expansive, or floating serenely in the microgravity environment of low Earth orbit. This constancy is a cornerstone of physics, a fundamental property that defines an object's inertia, its resistance to changes in motion. Unlike weight, which is a measure of the gravitational force exerted on an object, and therefore varies with location, mass is an intrinsic property. A rock weighing significantly less on the Moon than on Earth still possesses the exact same amount of mass. It does not evaporate, nor does it degrade over time. It is not susceptible to spoilage, nor does its quantity fluctuate based on your fluctuating mood. This unwavering permanence sets mass apart from many other physical attributes. A banana might ripen and eventually spoil, its chemical composition changing and its appeal diminishing. A balloon might deflate as air escapes, reducing its volume. But the mass of the banana, even as it spoils, remains constant. The mass of the rubber in the balloon, even after it deflates, is unchanged. It stands as one of the very few physical properties that stubbornly refuses to be situational, consistently asserting its inherent quantity, regardless of external circumstances. This makes it a crucial variable in countless scientific equations and models, from calculating the trajectory of a spacecraft to determining the energy released in a nuclear reaction. In countless ways, mass serves as the quiet, yet immensely strong backbone of reality, meticulously shaping our world through its unwavering consistency. This fundamental property dictates how objects interact with each other and with forces. It is evident in the resistance you feel when smoothly swinging open a heavy door, requiring more effort to overcome its inertia than a lighter door. It's present in the comforting sensation of your car steadfastly hugging the road during a turn. The greater the mass of the car, the more grip it can potentially exert, influenced by friction and other factors. And it's undeniably present in the unwavering firmness of the ground beneath your feet, as the Earth's immense mass creates the gravity that anchors us. From the smallest subatomic particles to the largest galaxies, mass is the unseen architect, influencing everything from the collision of billiard balls to the orbits of planets. It may often be invisible to the naked eye, but its presence is never ever absent, continuously defining the physical world we inhabit. Understanding mass extends far beyond merely memorizing physics equations. It delves into appreciating the subtle yet powerful forces that intricately weave the tapestry of our existence. It offers a profound realization that the world we inhabit, the very reality we perceive, is meticulously crafted from both immense cosmological interactions and the most minute fleeting engagements. This understanding teaches us that even the simplest, most mundane experiences, like the quiet act of lifting a warm cup of tea, are deeply rooted in elegant and profound scientific principles. Mass, though often operating silently and imperceptibly, speaks volumes about the very fabric of our universe. It dictates the strength of gravity, the force that binds galaxies and planets, and the reason objects fall to the ground. It is fundamental to the concept of inertia, explaining why a massive train is harder to stop than a bicycle. Furthermore, mass is inextricably linked to energy through Einstein's famous equation, E=mc², revealing that even a tiny amount of mass can be converted into an immense amount of energy, a principle at the heart of stellar fusion and nuclear power. From the subatomic particles that constitute everything around us to the colossal structures of the cosmos, mass is the underlying constant, the silent architect shaping every interaction and defining the very essence of matter